Okay, so let's start the third lecture. Calling Cristopher, our first online speaker, who is going to continue the talk by Martezik, the same title, Darboux relative exactness and pseudo-Abelian integrals. So Colin, please.
Okay, can you hear me okay?
Yeah.
Yeah, thank you very much. And thank you very much for the invitation. I'm very sorry that I couldn't come in person, but personal reasons have made it quite difficult to travel at the moment. So I had to ask Hossein that we could deliver online, which he was very kind to let me do that. So I'm going to start by just picking up where Pavel left off and give a brief summary of what we've done so far. And then I want to do a slightly more technical lecture this time to tease out some of the properties of Darboux relative exactness to prove the three corollaries that Pavel mentioned. And then if we have a little bit of time at the end, just to start setting up to show the proof of the theorem one, the main theorem, in the special case of just invariant lines. And then Pavel will return and sketch the proof in the more general case, which is a lot more technical. So we have the system we had already. So we've got omega is our one form that we're interested in. I'll explain the notation in a second. So f is my Darboux first integral. So it's going to be the integral, the product from I equals 0 to d of some polynomials to some powers. M is just going to be the product of those polynomials to the first power. And in this lecture, we're going to also use this notation M going to be the product of all the f's not equal to k. So in other words, it's just going to be M divided by fk, which we'll use later on. And in that notation, we find that my one form is omega is going to be a sum of lambda I dfi and times by mi. Okay, so this is my logarithmic foliation or my Darboux foliation. And we've been looking at having a perturbation. So omega epsilon is my omega plus a small perturbation term. And we want to try and bring that to the form that we're used to, which this expression. And here, this is just the derivative of the sum of lambda I times the log of fi. In other words, this is a Hamiltonian system now, and we know that the limit cycles are given by the integrals of the perturbation term over the vanishing cycles. So in this case, the vanishing cycles are going to be a family of loops around a critical point. And we're always going to assume that if these are the curves, the invariant curves that make up the Darboux integral, we're always going to assume that we're away from those curves. So that, in particular, this vanishing cycle here doesn't actually loop around any of these curves, fi equals 0. And so we want to be able to calculate this object around these vanishing cycles, and we're going to call this I of t. And our interest is mainly in when I of t is identically 0, because it's going to allow us to give some sort of estimates on the number of limit cycles we can bifurcate and many other things. So that's where we got to with Pavel. And then we also mentioned three generic assumptions. The first one is that the fi equals 0, the algebraic curves, together with the line at infinity, form a normal crossing divisor. In other words, each of the curves itself are smooth, and where they intersect transversely. Second condition is that the ratio of the eigenvalues are irrational. And if we also want to include the line at infinity, we also need something like the sum of the lambda i's times the degree of the curves over each lambda k is also irrational, because that's effectively the multiplier of the line at infinity if we homogenize the Darboux first integral. And the third condition is that the critical values away from the curves fi equals 0 are all distinct. So this gives us some control over how when we transport the curves around the vanishing cycle, we have enough control to be able to generate the quantities we want. And as Pavel explained, those quantities are actually integrals around Pochhammer cycles. Okay, so the main theorem is the following. If these conditions hold, then we can say the following. If the integral of eta over m is identically 0, then it implies that eta over m is Darboux relatively exact, which means we can write it in the form that Pavel's already given before. So this is the idea of being Darboux relatively exact. And if we just look at this for a moment, we can also see if I'm integrating, if something is Darboux relatively exact, then clearly if I'm integrating along cycles, omega is going to be 0 because we're integrating along omega equals 0. So this is going to be 0. This term obviously is going to be 0 because it's exact. And this term will also be 0 because although potentially if we wound around a separatrix, we'd get something that's non-zero. Because our vanishing cycle here doesn't wind around any separatrix, as we transport it, it will maintain that property. And so this term here will constantly be 0 as well. So we also have an if and only if statement here. Okay, so we're going to prove that in a special case in the next session, but for the moment, I just want to concentrate on 3 corollaries of that, which Pavel also mentioned. First corollary is the following. As we learned in the first lecture today, there's a center variety, so there is various components made out of different things. So there are components made out of logarithmic terms. So there's a component in particular that's made out of invariant curves where the degree of this is bounded. Let's say the degree of this is less than or equal to ni, and there's a family of these things. And the first corollary is that when we perturb, if this thing is 0, then the perturbation is actually going along the direction of this family of Darboux integrals. In other words, it tells us that we get a complete component of the center variety in this case. So that's the first corollary we're going to look at in a moment to see how that comes out of the Darboux relatively exact condition. Second corollary is, now we know what gives zeros here, we should then be able to count how many terms we've got left. And so we ought to be able to estimate the number of limit cycles. And in particular, we will show in the case when omega has n plus 1 invariant lines. So the degree of omega in this case is n. We can have n squared minus 2 limit cycles around a critical point by perturbation. And the third corollary is a generalization of Francoise algorithm, which is we call the Darboux-Francoise algorithm. And that basically says, as Pavel was explaining, if we know that the first few Melnikov functions are 0, so we're looking at higher order terms of the return map, if we know that these terms are 0, then it turns out the next term can also be expressed as a pseudo-Abelian integral of the form eta over m to the k now times some polynomial ek minus 1. And that again follows exactly from the Darboux relatively exact condition. Okay, so that's what we want to do in this lecture. And so the first question I want to ask ourselves is, what does the Darboux relatively exact condition imply? Because there's something to tease out here a little bit, because it's not quite as obvious as the relatively exact condition. So let's take the more general case. So I'm going to write this down. So this is now p to the k, m to the k plus 1 times omega plus d r over mk plus 1 plus sum of alpha I dfi over fi. So we notice immediately that these terms here potentially have something of the order 1 over fi to the k plus 1, whereas over here it's just like 1 over fi to the k. So there needs to be some cancellation. These two things, p and r, are not, we can't choose them arbitrarily. We need to tease out a little bit about what's going to happen here. And that gives us an alternative formulation for Darboux relatively exact, which we can then use to show our corollaries. Okay, so let's multiply this expression here by m to the k plus 1, and we'll get m eta is now p times the sum of I equals 0 to d of lambda I dfi mi mr minus k times sum dfi mi r plus a remainder term over here, which is I dfi. Okay. And here the idea is that if we just concentrate on one particular curve and look at when fk is equal to 0, what we'll find out is that lambda I times p minus k times r is equal to fi times hi for some polynomial hi, because the way this vanishes, I'm going to find that fi divides just the terms in p and r. And that's because when I put this equal to 0, I'm going to get lambda I times p minus k times r times df, lambda k should be there, dfk times mk is equal to 0. And obviously, from our conditions, we can cancel those out. And I know that this is equal to 0. And so therefore, I get some expression about lambda k times p minus kr is equal to fi. Actually, there should be k's as well. If I take two different values of this, let's take k equals I and k equals j, then I've got this expression for both I and for both j, and what I'll end up with is lambda I minus lambda j times p is equal to an expression like that, and the same for r. In other words, both P and R are in the ideal generated by Fi and Fj, for all I and j with I not equal to j. So now let's look at the following ideal. Let's take the ideal generated by M0, M1, up to MD. Remember, these are the M's divided by the product of all the F's apart from, for example, apart from F0 or apart from F1 and so on. Then what do we have? We have that if M0 equals M1 is equal to MD is equal to 0, then that must mean that two of these curves, Fi and Fj, must be equal to 0 for some I and j with I not equal to j. But that implies that P and R are both equal to 0 because of these conditions up here. And by the non-Stellar stats, that means that P to the n and R to the n are both in my ideal I for some sufficiently large n. Okay, but we have something else, because my condition G1 actually implies that the at each critical point the linear terms of the ideal generated by M0 to MD are independent. Sorry, not independent, but they generate the linear terms so that implies, by using the AF plus BG theorem, that in fact we can choose n is equal to 1. So in fact P and R are both in my ideal I. And so we can write P as being a sum of AI MI, and R is equal to a sum of BI MI for some polynomials AI and BI. We then want to plug that back into the conditions that we've already got. And with a little bit more work, we find that in fact we need some more conditions here, which is that lambda I AI minus k times BI must be divisible by Fi, and there must be another polynomial Ci, which gives me this condition here. So this is just by taking these expressions here and plugging them back into this condition here. And after a little bit more work, we finally get a final expression for P and for R, which is that P is going to be equal to minus K times HI times MI plus H times M. And R is going to be the sum of lambda I times HI times MI plus H prime times M, where in fact the HIs are just my BIs over lambda I's, and my H is the sum of CI over lambda I, and H prime is equal to 0. Okay, so this is, if we do have a relatively exact, Darboux relatively exact expression, then in fact in general we can choose P and R to be in this form, where the HIs and the H's are, and the H prime are polynomials. And we could have used that as the definition for Darboux relatively exact, but it's a little bit less transparent than the other one, but this one's actually very useful when we're trying to do applications. So let's just take the case k equals 1 and rewrite the expression that we've got for eta now. Eta will be equal now, for the Darboux relatively exact case, to be omega times minus the integral of hi over fi plus h plus d of the sum of lambda I hi over fi plus h prime plus the sum of alpha I dfi mi. And if you calculate this and you look for the terms in 1 over fi squared, you'll notice that the terms that appear here and here cancel out now. And so there's no squares. 1 over fi terms here cancel out and everything is nicely well behaved over here. Okay, so this is an alternative way of considering Darboux relative exactness. And what we'd also like, as somebody mentioned, was do we have degree bounds on this? And it turns out it's fairly easy now to get some degree bounds. And we can take the degree of h to be less than or equal to the degree of eta minus the degree of omega, and the degree of the hi's to be less than or equal to the degree of the fi's plus the degree of eta minus the degree of omega. In other words, the natural bounds that we'd expect hold here. Okay, so having done that and having got some degree bounds, let's now go back and look at the corollaries that we claimed that we had. So first of all, corollary 1, we want to find a perturbation which is also Darboux. So we've got our system, omega plus epsilon eta. We want to try and represent that perturbation as coming from a Darboux perturbation. So let's first of all try the general case. So here we're not assuming any degree bounds on eta. So it could be, the degree of eta could be bigger than the degree of omega. So we're expecting a little bit more wild behavior here. In particular, we might get some other things appearing in our Darboux integral. For example, there might be an exponential factor. We might get some other curves appearing. So for example, this is a curve 1 plus epsilon h equals 0, which vanishes when epsilon equals 0. So this is like a curve that comes in from infinity as you perturb. And then there's going to be a product of my original curves with a perturbation term. And also we're going to allow the exponents to also change. We also need to redefine m now. So m is going to be the product of all the curves to the power 1. But because this is a new curve, we need to add it here as well. So this is going to be the product from I equals 0 to d of fi plus epsilon hi. And then if we work out what we're left with, we take omega epsilon to be m epsilon times d f epsilon over f epsilon. So this is the perturbed system in this family of Darboux first integrals that we wrote down over here. It turns out to be my original omega plus epsilon eta tilde plus some order epsilon squared terms here. Okay. So what is this eta term here? It turns out that if we did the calculation, eta over m is just to the form omega over m times minus the sum of hi over fi plus h plus the sum of lambda I dhi over fi plus dhi prime plus the sum of alpha I dfi over fi. In other words, it's exactly the right form for our Darboux relatively exact perturbation. So in other words, every Darboux relatively exact perturbation can be realized in some extended family, which might involve the appearance of an exponential factor and also the appearance of a new algebraic curve, like that. However, if we take that the degree of eta is less than or equal to the degree of omega, then we can use our degree bounds to simplify this a lot. So the degree of hi now must be less than or equal to the degree of the fi's, and we must have that h is a constant. So and it turns out that if h is a constant, then I can absorb it into this factor over here. So in fact, we can take this expression, we can remove the hi, we can keep the degrees of these nicely bounded, and what we end up with is just the following perturbation. F epsilon is now just the product from I equals 0 to d of fi plus epsilon hi, so lambda I plus epsilon alpha I, and m epsilon is just the product of I equals 0 to d of fi plus epsilon hi, where the degree of hi is less than or equal to the degree of the fi's. So in other words, this perturbation, if it obeys the degree bounds, actually lies within the family that we're expecting. So we've got a complete family, and it forms a nice component of the centre variety, and it's also reduced in some sense. So the perturbations are effective as we move away from that. So that's corollary 1. Corollary 2 asks how we could actually use this effectively for doing perturbations. So how do we actually use this information to generate limit cycles? So we're interested in the following. We're interested in the number of effective, or we want, if you like, the dimension of the effective perturbations of in the form omega plus epsilon eta. In other words, we're looking for the dimension of the perturbations where eta over m on my family vanishing cycles is not identically 0. So what was it likely to be? Well, we've got, in terms of if the degree of eta is less than or equal to the degree of omega, let's say that's n, then we've got n plus 1 times n plus 2 parameters which can characterize eta. So the dimension of the space of one forms of degree n is going to be n plus 1 plus n plus 2, minus, we need to take away the dimension of the space of etas such that the integral of eta over m over my vanishing cycle is equivalent to 0. And of course, this is just the dimension of etas which are Darboux relatively exact. So in the general case, we can calculate these things, but we wanted to have one particular example, or one concrete example, to see if the number of limit cycles we could generate was actually a good estimate. So I think in the original paper by Ilyushenko, when he was doing bifurcations for Hamiltonian systems, he got something like an order n squared over 2 bound on the number of limit cycles by counting the number of effective perturbations, and we wanted to try and do the same thing here. And so we're going to make the assumption that we've got n+1 invariant lines. And so that means that omega has degree n. And we're going to assume, obviously, that G1, G2, and G3 hold, which is a generic condition anyway, so that's fine. And we want to estimate what is the dimension of the number of Darboux relatively exact one forms that we have. Okay, so let's try and do that. So we've got eta over m from the formulas that we've done before is minus omega over m, the sum of hi over fi plus h plus the sum of lambda I d hi over fi plus sum of alpha I d fi over h. And here, to start with, we should put the full form. But because we're making the assumption that the perturbation has degree less than or equal to the degree of omega, we can see that h prime is a constant. So that's going to disappear. H is a constant, but it can get absorbed into here. So we can assume that this is also gone. And then we need to count up how many parameters we've got left. So we know that the degree of hi is less than or equal to the degree of fi, but because it's a line, that's 1. So I've got effectively 3 parameters for each hi here. And I've got 1 parameter for every alpha I over here. So I've actually got 4 times n+1. So each curve gives me 4 parameters. So that's the number of parameters that I have available for eta over m. But some of those are going to be overcounting. So we need to look at how much we're overcounting here. So we need to look at what's the dimension of the space where minus omega over n times the sum of hi over fi plus lambda I d hi over fi plus the sum of alpha I dfi over f is equal to 0. How much overcounting have we done here? Well, if we look at this expression, we can take the exterior derivative of it. Clearly these 2 terms will vanish because they're, and we're just left with minus omega over m. D of omega over m is 0. So what we end up with is omega over n wedged with d sum of hi over fi. But this is actually not possible because this is a Darboux, system has a Darboux first integral with irrational exponents, whereas this one here would imply that we have a rational first integral. And the only way that that's going to happen is that this must be a constant. In other words, this is only going to be possible if hi is going to be some constant times fi. So we plug this expression back into here. We actually find that minus omega over m, sum of the ki's, plus the sum of alpha I dfi over fi needs to be equal to 0, and that implies that for all r, alpha r is equal to lambda r times the sum of ki's. In other words, the amount of freedom that we have is we can choose these ki's, and once we've chosen the ki's, all the other parameters are fixed. And so the overcounting is in fact just n plus 1, because there are n plus 1 k's here. Okay, so the number of effective parameters, or the dimension of the effective perturbations is going to be n plus 1 times n plus 2 minus, we had 4 n plus 1, but n plus 1 of those is overcounting, so minus 3 n plus 1, and that turns out to be n squared minus 1. So we have n squared minus 1 effective parameters that we can work with. Okay, so we actually want to know that they generate limit cycles. What we'd really like is to be able to bifurcate the limit cycles from a critical point, but that's actually quite tricky to prove that. But if we relaxed our searching a little bit and just asked for generating limit cycles somewhere along a transversal, so if I take a transversal like Paval-Drew, and I want to know where the limit cycles appear, they're going to appear when, under perturbation to first order, when this thing is equal to 0. So if I call the, if I take an eta I for each of the expressions in this this space that I've got left, I'm going to have expressions I1 of t, I2 of t, and so on. Let's call that k as the total number, ik of t. And normally what we do then is we try and find some nice properties. So for example, the Chebyshev property, which is that if you have a Chebyshev property over an interval, then you can generate that number of limit cycles in that interval. So what is the Chebyshev property? The Chebyshev property, we take the expressions from I1 to ik of t, and then we take their derivatives up to k minus 1's derivative of these things. And then we want this to be single-signed, either greater than 0 or less than or equal to 0, sorry, greater than 0 or less than or equal to 0 in an interval. So in particular, all we need is that if we can find some period annulus where inside that period annulus we have this inequality, then we know we can generate that many limit cycles. In fact, we can generate this number minus 1 limit cycles inside that region. So that's always going to hold the case unless this thing is identically 0, unless this determinant is identically 0. But you can show that if this determinant is identically 0, then in fact there's a linear dependence between these quantities here, and if there's a linear dependence between these quantities, then in fact that contradicts the assumption that they're linearly independent. And so we can always find a period annulus where we can generate the dimension of the system minus 1 limit cycle. So in other words, it implies that there are n squared minus 2 limit cycles in some period annulus around a critical point after perturbation, after some choice of perturbation. And that seems to be quite a good estimate. I don't know if taking different degrees of curves and that would make a better job, but that seems to be quite a good estimate for the number of limit cycles around a critical point. And the final corollary we wanted to look at was the Darboux-Francoise algorithm. So I wanted just to remind very briefly about what the Francoise algorithm is, and then say how we can generalize it. So when we have a perturbation of the form omega epsilon is equal to omega plus epsilon eta, it's not uncommon to find that the first Melnikov function is identically 0, and then we want to be able to know something about what's the next Melnikov function, and so on. And the Francoise algorithm says that, in fact, this can be done in a very nice way if we know that we can write our etas as relatively exact functions. Okay, so the Francoise condition star is the following. It's a condition on the Hamiltonian system, on Hamiltonian systems, to say that if we have the integral of eta equivalent to 0 around a vanishing cycle, then eta must be relatively exact. So in the Hamiltonian case, it's something in this form for A and B polynomials. And then what Francoise noted was that if you do that, then your perturbation now could be written in the form dh plus epsilon A dh plus dB. And then with a little bit, if we pre-multiply by 1 minus epsilon A, then we get a dh term, we get an epsilon dB term, and we get a minus epsilon squared A eta term. So if I'm integrating now along my perturbed system, this thing is exact, this thing is exact, and so this term here will give me the second order perturbation term. So this will give me minus A eta, will give me my second order term for perturbation. In other words, it's also an abelian integral. And that can be iterated to any number of terms. So if we took, as we work along, we'll end up with an expression like this. And we'll get dh plus epsilon dB1 up to epsilon to k minus 1 dB k minus 1. And then there'll be a final term, which will be epsilon to the k, epsilon to the k minus 1 eta. And then if we look at this term, all these things are exact, and so my mk will be equal to the integral of minus ak minus 1 eta if m1, m2, mk minus 1 is equal to 0. So we'd like to do the same thing for our Darboux relatively exact sequences as well, and it turns out to be almost identical in idea. So let's just take the first couple of terms and then see how that works. So my first Melnikov function is going to be of the form eta over m, and that means if this thing is identically 0, that means I can write eta over m as p1 over m omega over m plus dr1 over m plus sum of alpha I1 dfi over fi. And so I rewrite this expression just as we do with the Francoise algorithm in the following form. This is going to be df over f plus epsilon dr1 over m plus sum of I1 dfi. fi minus epsilon squared, and here I'm going to have P1 eta over m squared. So again, this bit's going to be something which is exact, because I'm not cycling around any of the separatrices. This thing is also going to be 0. And it tells me that if m1 is identically to 0, then m2 can be written as the integral of minus p1 eta over m squared. So this is also a pseudo-Abelian integral. And then we can carry on the same process. So we now know that this is, we can now write this as from P2 over m squared times omega over m plus d r2 over m squared plus the sum of alpha I2 dfi over fi. And again, rearranging things a little bit, we'll get the next term, just like in the Francoise algorithm. So we get the initial term plus the term we had last time, which was d r1 over m plus the sum of alpha I1s dfi's over fi's, plus the second order term, which again is exact, plus now a third term, which will now represent my m2, so this will be epsilon cubed p2 eta over m cubed. So if m1 is equivalent to m2 is equivalent to 0, then my m3 will be equivalent to minus, equal to, minus the integral of p2 eta over m cubed. So at the cost of this increasing power of m at the bottom, we still get this property that our higher order terms can be obtained in terms of pseudo-Abelian integrals. I'll just mention one more thing, which is we can generalize this a little bit. So the Francoise algorithm just asks for a first order perturbation, but we could ask, does the same thing hold if I had higher order perturbations? So supposing I just had an analytic series of perturbations, what can we say about the Melnikov functions? In this case, it turns out you can do exactly the same thing. So if m1 is equivalent to m2 is equivalent to mk minus 1 is equivalent to 0, then there exists some one form eta k such that my kth order Melnikov function can be written in the term eta k tilde over m to the k. And so I have a nice way that I can then iteratively write out all the terms of my expansion purely in terms of integrals of pseudo-Abelian integrals. Okay, so that was the proof of the three corollaries. What I want to do now is to start moving on to what happens in the case of just when we have just lines, and we're getting towards the time when we're supposed to be finishing. So perhaps rather than starting something new, I think I'll stop there, and then the next lecture explain how we get the case of just the invariant line case, and then Pavel will generalize that to other curves of higher degree.
So you still have 5 minutes, I think. You want to go?
5 minutes?
You have still 5 minutes.
Okay. Let's make a start. So so here we're looking at some curves, some lines now. So the degree of fi is going to be to 1 for I equals 0, 1 up to d. and I'm going to call the line Li is just going to be the zeros of Fi. And we've also got a line at infinity. And the idea is as follows. We're going to concentrate on what's happening in a neighborhood of the line L0. And then intersecting that line, we're going to have the line at infinity and the other lines, L1, let's say L2, L3, and so on. And as Pavel explained, what we'd like to do is we'd like to integrate around this. We'd like to find an expression for that R over M to the K by integrating around loops in here. But the loops are multi-valued, so we need to find some way of removing that multi-valuedness. But let's just set this up for the moment. So around each of these singular points, I'm going to have a path. So let's call that A1, A2, A3. And there's also going to be an A infinity. And I'm going to take an integral. The integral is going to be, let's say, tk will be the integral of eta over m around the loop ak. And I want to try and find some way of dealing with this. And the way that we're going to deal with that is that, in fact, we're going to show that the integral of eta over m vanishes along every Pochhammer cycle in close to this curve L0. And what that's going to mean is if we define a variation, so variation of lambda of some function f of c is going to be f of c times e to the 2 pi I lambda minus f of c. We're going to find that having an integral around of eta over m equals 0 around a Pochhammer cycle actually implies that the variation of lambda I, where this is going to be some expression associated, so each of these is going to have some lambdas associated to them. We'll come back to that in a while. The variation around lambda I of t k will be the same as the variation around lambda k of t I. That's actually the Pochhammer cycle condition. And from this one, we'll find that we can reconstruct my integral by, first of all, as Pavel said, we can construct around a neighborhood of infinity because it's a node, and so it's trivial to construct a solution system, and then we can extend it to a neighborhood of the line, and then we can use this fact that the complement of the line is a Stein space to actually extend that to the whole space, and then that will give us our result. So we'll start from there tomorrow and try and give a sketch of how this works in this case.
Okay, so let's thank the speaker. Any question? Maybe I ask one question. Colin, you are as far as I know, the record holder of lower bound for limit cycles, in a different context, not Abelian.
Yeah.
Is it for me? Is it possible to combine that method, your older article, and this method of Abelian integrals to get better lower bound for the number of limit cycles? Do you think?
Yes, I mean it depends. Yeah, I mean the sort of n squared log n bound was just a Hamiltonian system, so in theory it would be you could get better bounds. Whether you could get ones that had a higher order of growth, I don't know. I mean the Darboux integrals certainly provide very high orders of cyclicity. But unfortunately, they're not the generic ones. They're the ones that are unusually high degree. So it's where there's some relationship between the various different curves which cancel out nicely. So you get a much higher degree than you'd expect. And those are very hard to predict. You can't sort of write them down easily.
Okay, so if there is no question, let's thank the colleague once again. So maybe I will